Coming up on Philosophy Talk.
Scotty, I can't change the laws of physics.
What goes up must come down. Spinning wheel, got to go round.
The laws of physics determine how things change in the cosmos, but what if the laws of physics themselves change?
Unless you people on the bridge start taking showers with your clothes on, my engines can pull us out of anything.
Would airplanes still fly if the laws of physics changed?
Could humans still exist if the laws of physics changed?
Would our whole world turn upside down if the laws of physics changed?
Would you still love me if the laws of physics changed?
Captain, what do we do?
Are the laws of physics really the same everywhere and everywhen?
Our guest is Massimo Pigliucci from the City University of New York.
Could the laws of physics ever change?
We're going down, Captain.
Coming up on Philosophy Talk.
What if gravity suddenly became twice as strong?
What if E gradually came to be equal to mc cubed rather than mc squared?
Could the fundamentals of physics really change like that? Or is this just the stuff of science fiction?
Welcome to Philosophy Talk, the program that questions everything.
Except your intelligence. I'm Ken Taylor.
And I'm Janan Ismail, sitting in for John Perry.
We're here at the studios of KALW San Francisco.
Continuing conversations that begin at the Philosopher's Corner at the Stanford campus, where Ken teaches philosophy, and where I visit occasionally for my home department in the University of Arizona.
And we're always thrilled when you do. Welcome back, Janan.
Thanks so much, Ken. Today we're asking whether the laws of physics could ever change.
Now, does this idea that the laws of physics might change even make sense, Janan?
Well, surely we can imagine such a thing. I mean, early in the history of the cosmos, fundamental constants have one set of values. Later they have a different set. It would be surprising, but the idea isn't incoherent.
Surprising? Come on, the Cubs winning the World Series. Now that was surprising. The strength of gravity changing? Oh, that would be,
Well, it would need some explaining.
Well, yeah, definitely. And what could the explanation possibly be? And don't say, well, even more fundamental laws could explain it.
Because then you'll say that the original laws weren't fundamental after all.
That's exactly what I would say. And then, I don't know, maybe I don't have enough imagination, but the only other possibility I can think of is that the fundamental laws could somehow explain their own evolution, but that seems kind of paradoxical.
Paradoxical is a bit strong. And you're thinking of it the wrong way. You're thinking that the universe is this big, ever-evolving totality. You're assuming that its evolution must be governed by a ground of kind of fixed, unchangeable laws that hold everywhere and everyone.
That is how I'm thinking about it. And you see something wrong with that picture?
Well, it's a lovely picture.
What do you mean? It's one we inherited from the incomparable Newton, by the way, Janan.
Right, and one that's worked well, up until now.
Up until now? You're suggesting that maybe we should abandon it?
What's left us with questions we can't answer?
Like what?
Well, like, why do we have just the laws that we have rather than some other set of laws?
Well, come on. There's no explanation needed for that. Fundamental laws just are. That's what you get when you get to be fundamental. You don't get explained. You do the explaining.
But our laws aren't just any old laws. They're really, really special.
Oh, come on. Special compared to what?
Look around you, Ken. They produce an amazingly complex and delightful universe. It's like it was designed by an architect with an incredibly rich imagination.
Janan, wait a minute. You're not going all creation scientist on me, are you?
No, Ken. I'm not talking about intelligent design. But think for a second about how amazing the mere fact of the universe is. If the masses of the elementary particles or the strengths of the fundamental forces had differed ever so slightly, the universe would be more like, a puddle than a vast and varied menagerie.
Well, yeah, I gotta admit, I'm glad we don't live in a puddleverse, that's for sure.
Right, but why don't we? Why are the laws, the constants, and the parameters tuned just right to avoid the much more likely and the much more easier to achieve possibility of a puddle universe, rather than yield the kind of vast, beautiful menagerie that we see instead?
I don't know, blind luck, I guess, Janan.
Ken, that's not an explanation.
Well, what, you want me to say, what, the multiverse? I don't like the multiverse.
Look, it's not a bad start. But if every possible universe is simultaneously actual, that's not quite special in the right way.
Oh, well, it sounds like you think you got a better idea.
Of course I have a better idea, Ken. Suppose that the laws, the parameters, and the constants literally evolve. The universe tries out lots of alternative configurations as small improvements get preserved. Over time, a universe with just the right laws, just the right parameters and constants, and just the right values eventually gets produced.
Wait a minute. Are we talking biology? That sounds like biology or cosmology. I thought we were talking about cosmology.
We're talking about cosmology, but evolutionary cosmology.
Evolutionary cosmology. You mean like with cosmic selection instead of natural selection?
Exactly. Cosmic selection gradually designs the universe in the way that natural selection gradually designs a bioverse. It preserves the interesting universes, and it discards the puddly universes.
No, survival of the fittest universes, eh? Come on, Jeanette.
You're catching on, Ken. The beauty of it is that without appealing to an outside designer, it answers the question, why just these laws rather than some others? Answer, a universe governed by them is more cosmically fit.
Gee, Jeanette, that's really interesting, but I don't know. Wouldn't a cosmic selection itself have to be governed by, laws? And wouldn't those laws be fundamental? And wouldn't we just be back in the soup of where the fundamental laws come from?
Ah, Ken, here I thought you'd come so far, but you're still stuck on Newton, aren't you?
Yeah, I have to admit it. It's hard to get over Newton. Once you go Newton, you don't go back.
Maybe this will help. We sent our roving philosophical reporter, Holly J. McD, to look at some places where the laws of physics do change, beginning with good science fiction. And she files this report.
Sidney Perkowitz is a retired physics professor who calls himself a recovering scientist. He loves the laws of physics and sci-fi movies. He says movie directors are constantly taking advantage of theories that say the laws of physics could change in a different universe with a different set of rules.
Often it's just a word salad, The attitude is if you throw in the words quantum mechanics, relativity, wormhole, black hole, you've covered it.
But then there's Contact, a movie that's basically about space aliens communicating with people on Earth. Perkowitz says it's a movie that respects the laws of physics. It's based on a book written by astronomer Carl Sagan.
This morning's detection of an unidentified radio source from deep space can neither be confirmed nor denied.
Whatever it is, it ain't local.
All the science that involves searching for alien life, the radio telescopes that search for signals and so on, all of that is well done. The part that's a little hairy, but within the realms of possibility, is traveling through black holes and wormholes and so on to different universes. We don't really know that we can do that yet, but on the other hand, we don't really know that we can't do that yet.
Once at a conference, Perkowitz casually suggested more movies be like Contact.
A science fiction film is great if it has to break one law of science to make the plot work, but then it works out logically what happens after that. But of course, some real science fiction fans emailed me or tweeted or whatever and said, how dare you take away our ability to break as many laws as we want?
The Science and Entertainment Exchange is one group that advises movie directors on ways to follow the laws of physics.
Someone will come to them with an idea and the scientific consultant will say, you know what, that isn't good science, but here's something that's even weirder and wilder. And sure enough, that'll end up in the film.
Scientists like Jeffrey West say the laws of physics make life more exciting.
It depends what you mean by the laws of physics.
West is a theoretical physicist in constant search of fundamental physical truths. He says that the laws of physics can change, but you need to be careful about defining the conditions
under which change can occur and the scale at which you're talking.
West worked for decades as a high-energy physicist at Stanford University, but now he's more interested in studying the laws that govern other areas, like biology and even cities.
Are there sort of Newton's laws of cities or Newton's laws of biology and so forth? What do we mean by that? What do we imply by that?
Recently, he set out to uncover the laws of cities. He discovered that if he knew the population of a city, he could make all sorts of predictions.
I can tell you with 10-20% accuracy almost everything about it. What the length of all those roads will be, how many police it should have, how many restaurants there are, how many lawyers there are, and so on.
Whether the place is Manhattan or San Francisco, he says, cities follow certain patterns. For example, after a city doubles in size, it experiences a 15% capita increase in crime, traffic, and AIDS cases. But if the pattern continues, West says, cities may also collapse.
They've built into them their own demise. And, are they such that we are able to change them?
In other words, the laws stay the same, but we can try to change the conditions where these laws are applied. For instance, we can innovate and turn to alternative forms of energy. Attempting to thwart the end of the world with data? That sounds like a science fiction movie. In fact, Sidney Perkowitz says that's why it's important sci-fi movies follow at least some of the laws of physics, to show us a world more like our own and how we can realistically change it for the better.
Right now in our whole society, our whole country, we're in a place where there are powerful forces who want to deny science. Okay, a science fiction film does not change our whole policy about global warming, but it's all part of the same picture. So you want to see science presented as clearly and correctly as possible, just as a general rule.
Some laws are meant to be broken, others are even more fun when we try to follow them. For Philosophy Talk, I'm Holly J. McDeed.
Thanks for that fascinating report, Holly, on breaking or making or whatever the laws of physics. I'm Ken Taylor. With me is my fellow philosopher and good friend Janan Ismail. And today we're asking, could the laws of physics ever change?
We're joined now by Massimo Pigliucci, professor of philosophy at Sydney University of New York, author of many things including Nonsense on Stilts, How to Tell Science from Bunk. Massimo, welcome back to Philosophy Talk.
Thanks. It's a pleasure to be back.
Massimo, you've thought and written about lots of different things in philosophy, science, and the philosophy of science. Why is this one worth thinking about? It's a kind of mind-boggling one. Why is this worth thinking about?
It's worth thinking about it for a number of reasons. First of all, because physicists themselves are thinking about it, and if they are sort of concerned or interested in the possibility that the laws of physics might change over very large spatial scales or temporal scales, then that seems to be an interesting question, especially for a philosopher of science who is somebody who tends to think about what scientists do and why they do it, right? But also there is the more fundamental curiosity that we all have. Why is the world the way it is, and is it going to change? And if it's going to change, in which way?
Massimo, the idea that a law of nature might change is probably alien to most people. Is there even a way of thinking about laws of nature that allows for the possibility that they might change?
Well, there is a way to think about the laws of nature in the sense that they might not be laws, after all. So the word law, of course, is a little bit problematic from a scientific perspective, right? Because it immediately brings up the question of, well, if this is a law, who or what decided that was going to be the law? And you guys mentioned Newton a lot before, and in fact, it was Newton that insisted that we should think in terms of laws of nature, that is, of never changing, parameters that describe how the world works.
You make that sound like a controversial idea.
It was, even at the time. So Newton was very much of a pious person. He was a very complicated person, but he was also a very pious person. Many people don't realize, for instance, that he actually spent more time writing biblical criticism than doing physics. But there were some of his contemporaries or people that lived shortly before him that were actually not that much on board with this idea of laws of nature. One of them was Galileo. Galileo thought that talk about law, maybe because he had too much of a close run-in with the Catholic Church, but the talking of law and therefore with immediate implication of a lawgiver was something that science really better stay away from it. And in fact, Galileo said, these are not laws; these are just empirical generalizations. This is stuff that we think we find out about the world by doing experiments in a very local and very idealized situation.
Massimo, is there a difference between calling something a law and just saying that it's a regularity that holds?
Yes, I think there is. It's not just a question of semantic, right? Again, it depends on how you interpret laws. But if by law you mean something that is completely, utterly, ever without any possible, change or exceptions, then that's a very strong statement. If you call it a empirical generalization, then the question immediately is obvious. It's like, well, under what conditions does that generalization actually occur? Could there be exceptions? Under what conditions are there going to be exceptions? And what explains those exceptions?
But it sounds to me like you're saying, tell me if I got this right, it sounds like you're suggesting that our contemporary conception of a law as a exceptionalist generalization that's projectable and all this stuff, that's something that emerged at a point in sort of intellectual history, and its emergence wasn't clean. It was kind of controversial and messy. Is that right?
It was kind of controversial and messy in the beginning of modern physics, right? So modern physics started out with Galileo and then Newton. And so we're talking about, of course, the 17th and 18th centuries, the beginning of the so-called scientific revolution. And then it was kind of taken for granted. I mean, today, physicists normally think, they've written about laws of nature for 100 years or 150 years without ever questioning the basic idea of it until recently.
So we're going to have to dig into the questioning and the basis for possibly questioning after a short break, okay? You're listening to Philosophy Talk. Today, we're thinking about the laws of nature and whether they can change with Massimo Pigliucci from the City University of New York.
What would happen if gravity suddenly became weaker or stronger? Or if the strong force that binds quarks together and makes matter possible suddenly became weak? Are such things really possible, or just the stuff of science fiction?
Rewriting the Book of Nature when Philosophy Talk continues. Losing everything can sure make it feel like the world stopped spinning, as if the laws of physics have changed. I'm Ken Taylor. This is Philosophy Talk, the program that questions everything.
Except your intelligence. I'm Jananis Mill, sitting in for John Perry, and we're asking, could the laws of physics ever change? Our guest is Massimo Pigliucci from the City University of New York.
So, Massimo, I want to ask you a forward-looking question, but I also want to see if I can tie it back to the thing we were talking about just before the break, because you were going to explain to us what a law might be such that conceivably it could change, because that's a little hard to get your head around. And then that's one part. But then the second part is, okay, what might convince us? Is there any empirical science behind the idea that the laws of physics might actually change or be changing? Or is this just, philosophers love thought experiments. Is this just a philosophical thought experiment that has no chance of being scientifically established? But why don't you start by telling us what a law is such that it might change?
So think about laws or talk of laws in any other field other than fundamental physics. So the rest of physics, like thermodynamics, for instance, or solid materials or something like that, or biology or sociology or economics or any other field other than fundamental physics. People have been talking about, all the specialists in those fields have been talking about for a long time about finding laws. I'm particularly familiar with the biology part of it because I'm fundamentally a philosopher of biology. And, biologists, ecologists for a long time have been trying to talk about laws. But in fact, every time you look into what they mean by that, they mean in empirical generalizations that is known already. And if it's not known already, it will soon turn out to be prone to exceptions. And that these empirical generalizations are simply what happens if certain conditions hold. Right. But as soon as a certain number of conditions change in whatever reason, in whatever way, for whatever reason, then you get the exceptions, right. Or even you get a completely new pattern.
So in what sometimes are called the special sciences, there are law-like things, but they hold within certain boundary conditions. Those boundary conditions themselves can change, or they hold within a certain kind of dynamical situation. That dynamical situation can itself evolve, and the system can get more complex, and then the dynamics of it gets described by a different equation or something. And perhaps is the idea, perhaps the laws of physics are like that.
That's the idea. And the interesting part of the idea to me is that this has been arrived at, as far as I can tell, independently by a certain number of philosophers and a certain number of physicists. The two that come to mind most obviously, the two or three that come to mind most obviously are Nancy Cartwright and Ian Hacking on the philosophy side, and Lee Smolin, for instance, on the physics side. So these people independently. Yeah, go ahead.
Oh, it's my understanding that people like Cartwright who think about things like this.
These are famous philosophers.
Famous philosophers. It's partly because they deflate the idea of laws of nature. So they really have something quite different in mind when they're talking about laws than most people do. Is that not right?
That is right. I mean, Cartwright and Hacking are consider themselves empiricists. And the idea is, if you're an empiricist, that is, if you don't think that you can derive knowledge about the world somehow a priori just by thinking about it, then you have to go with what the data tells you. And how do we derive the laws, what we think are laws in science anywhere, not just in fundamental physics? Well, by doing experiments, repeating experiments, doing observations, and then we generalize. So in other words, we do something that it's that's referred to normally as inductive reasoning. And there's one thing we do about inductive reasoning, generalizing from individual instances or groups of instances to broader and broader categories, is that it's fallible.
So, look, okay, you guys are having a great debate. There's two different ways of thinking about how the universe evolves, fixed unchanging laws, or something more exception-prone and possible changing, subject to boundary conditions and all that. But I want to know, though, about how would I go about convincing myself by observing the universe that I was in a universe in which the laws were evolving? What would convince me of that, other than a philosophical a priori argument of some kind?
Well, that's how people like Lee Smolin, who is a physicist at the Perimeter Institute in Canada, come in, right? So he has written a couple of books about this that actually has to do mostly with the nature of time, where he argues that, in fact, there are ways of testing these kind of hypotheses. It's very difficult, but there are ways of testing it, because if some parameters of the known laws of physics should change, such as, let's say, like gravitational constants, we ought to be able to observe these very small changes if we look at either very distantly in the past or very broadly at a cosmological scale in space.
Has he
when you
sorry. I was just wondering if he's actually gathered any evidence, or if anybody's actually tried to find a way to test his predictions.
He has gathered evidence, but the evidence is, of course, as you might imagine, controversial. So at the moment, as far as I know, this is a minority position within physics. But Smolin does claim that there is evidence, and that evidence at the moment can be interpreted more than one way. And that's why people, I suppose, are not convinced.
Is this something that people should worry about? I mean, I'm partly wondering whether, imagine something like the gravitational constant changed. Our buildings would start falling. Maybe we'd start floating off the surface of the Earth. I mean, is this something to be seriously taken, into account in terms of planning for the future?
No, I wouldn't get a differently built house at the moment, just yet. We're talking about changes on a very, very long scale, or a very, very large spatial scale. So nothing that is going to have any effect whatsoever in our lives or the lives of our children.
But let me ask you a question, though, because there are, I don't know if you call them parameters. There are the things that change over different regions of the universe. Some quickly, some radically. Temperature changes, right? If it turned out that gravity, and temperature obviously isn't a fundamental thing, if it turned out that gravity changed over different configurations of the universe, wouldn't we have to just reinterpret what gravity is? It's not a fundamental constant. It's some kind of, I don't know, a scalar thing, which can have different values at different places. We think the laws that we have are fundamental, but they aren't really, it turns out, because these parameters can change. These constants can change. They can, right? They take on values at different configurations of something. I mean, is that a naive question? Or
No, that's a great question, and that's actually, I think, exactly how some people are thinking of it. And one of the reasons to at least entertain the idea is, in fact, using induction. So these, again, generalizations from past experience on the development of science itself and on the development of physics itself. I mean, again, let's go back to Newton. Newton thought that these laws were, in fact, fundamental. Right? Turns out that was not the case. There were actually empirical generalizations that applied, as it turned out, to a far more restricted sort of chunk of the world than Newton thought possible. So now, then when that happens, and this has happened several times in the history of science, and whenever that happens, then we say, oh, well, there must be something more fundamental. Right?
Well, we actually
but then again, one answer would be, well, but it's all elephant all the way down then.
Yeah, right. You're listening to Philosophy Talk. We're talking about whether the laws of physics can change. We'd love to have you join this conversation. Henry in San Francisco is on the line. Welcome to Philosophy Talk, Henry. What's your comment or question?
I'm going to politely question your intelligence.
Okay.
In 1978, Thomson Gregory, two scientists, discovered the CBM cold spot, or supervoid, which is empty both of dark matter and it's just a white void. The laws of physics absolutely do not apply here, and this debunks Arvo Penzi's and Robert Wilson's 1964 Nobel Prize theory that background radiation is detectable everywhere. What's wrong with that is we haven't been everywhere to make that kind of pronouncement, and we've barely left the neighborhood. And absolutely, the laws of physics most likely don't apply several 100,000 light years from here in this super void.
Henry, if I may, though, there's a difference between our beliefs about the laws of nature changing, which nobody has any question about, and the laws of nature themselves changing. Do you think that there's not a distinction there? And why is that not an example of our beliefs about the laws of nature, the known laws of nature, being wrong?
Well, the super void completely throws out our whole parameters. There's no dark matter. To our telescopes, it's a complete white void. It would suggest that there's the laws of physics just don't apply there.
Well, yeah, but Massimo, I think Janan's point still holds. Thanks for the call, Henry. It's a very stimulating one. Massimo, you got a response there? I think Janan's point still holds, though.
Yeah, I think it does, and I have a comment more than a response. That is the existence, postulating, for instance, dark matter and dark energy, which are, by the way, at the moment, the estimate is they represent a large chunk of the universe that we don't really know anything about. That's why we call it dark. That kind of postulation, which is pretty recent in modern cosmology, in modern physics, is in fact a symptom of the fact that we know much less than we would like to know about how the universe is structured. Now, is a way to explain, essentially the missing matter, is the best way to explain that, to postulate that the gravitational constant changes at cosmological scales? Well, that may be one way to look at it. It may also be true that in fact there is other types of qualitatively different types of matter that we just can't see. So that's the thing. The data currently clearly underdetermined. That is, they don't specify the answer to that kind of question.
So let me ask you guys both a question, though. I get the concept of fundamentality. I think it's an important concept. But what I don't quite know is whether we could ever have any confidence, epistemic, well-confirmed confidence that we've reached the ground floor. Newton apparently thought he reached the ground floor, and then Einstein came along. Then dark matter and dark energy. I mean, it turns out, gosh, we couldn't have reached the ground floor because there are these regularities that there wasn't enough gravity or something. So how would we be assured that we've reached the ground floor?
I think the thing nobody doubts right now, no physicist worth his salt doubts right now, that the known laws of physics aren't the true fundamental laws for lots of reasons. But a lot of them will say that the very practice of science is predicated on the idea that we should keep looking, and what we are looking for is the fundamental laws. That is, the fundamental laws are precisely those exceptionless regularities that govern counterfactuals, that hold always and everywhere. It's the holy grail of
So wait a minute.
science.
So what would be different about the enterprise of science, about the way we conduct the enterprise of science, if we did not have this confidence that comes from I'm not sure where, something about our conceptual scheme, that there is a ground floor? How would science look differently without that?
Yeah, I think they wouldn't look different at all. In fact, the only thing that would look different is fundamental physics, because the rest of science is already on board with that idea.
How do you mean that? Elaborate. That's an intriguing thought. Janan's shaking her head here. So elaborate, and then she's going to come back at you.
Sounds great. So the rest of science doesn't look for fundamental laws of even domain-specific fundamental laws. Biologists are perfectly happy to say, look, these are the empirical generalizations that we understand. We understand that to a certain point, and the parameters may change, the boundary conditions may change, and then we'll see how that works. So it's a very empirically, very hands-on kind of approach to things. And almost every scientist, except fundamental physicists, are perfectly fine with that sort of approach. It's just in fundamental physics, and that I think I blame, if you allow me to use that word, Newton for that. It's only in fundamental physics that we have this obsession that we gotta get to the bottom. What if there is no bottom?
So, Janan, what do you think? Come back, Janan.
No, I agree with most of what you said about the other sciences, but the practice of physics for sure would change. Much of what this sort of search for the fundamental unifying theory is supposed to do is organize the rest of science, which is taken precisely to describe sort of local laws, sort of relativized to certain values of certain quantities, or effective theories that hold under particular constraints. If there is no unifying fundamental science, then the ways in which those sciences themselves relate to one another would change.
But doesn't the multiverse hypothesis and the growing popularity already say, well, yeah, the universe is a kind of configuration among many possible configurations with many different boundary conditions, with many different initial something or other, and maybe we don't walk through all the multiverses, but once we allow the multiverse, haven't we already gone part way to that?
Yeah, I think that Ken has a good point here. So, and
She
I'm
doesn't.
not. I speak as well. I speak as somebody who actually is not particularly fond of the idea of the multiverse. But and maybe we can get into that later. But the thing is, if in fact we do allow that idea, one of the reasons a number of physicists don't like the idea of the multiverse is precisely what Ken is getting at, which is at that point there is no such thing as a fundamental law. It's just to throw the dice. All the different multiverses are just random combinations of parameters, and that's all you get. And therefore, fundamental physics would evaporate as if it is, in fact, understood in the way in which Janine was saying, and I think she's right, physicists have tended to understand it since Newton.
So, Jan, and then we'll let a caller in.
I mean, there's a number of different ways in which people understand the multiverse. So if you're talking about the multiverse as the ever-ending interpretation of quantum mechanics, then there is such a thing as the laws that govern the evolution of that large, collection of universes that are now constituting all of reality. I mean, there's very little difference between the way that the fundamental dynamical laws work with the quantum multiverse and the way that they do quite generally with, say, Newtonian mechanics and with classical physics.
So let's get a caller in here and see if we can get him in before the break. Bill in San Francisco. Welcome to Philosophy Talk, Bill.
Yeah, good morning. I'm thinking of what would happen if, let's say, that the caldera of Yellowstone were to go and create all this buffalo fondue or buffalo flambe, and then you have almost a domino effect, that affecting plate tectonics.
Yeah.
And let's add in some, areas that have been fracked so that this creates a kind of domino effect. Wouldn't something like that, or 200 million years ago, when, as our friend in New York who's on the phone might have heard, the Palisades separates North Africa from North America, as they start drifting apart.
So thanks, Bill. You're asking an interesting question, but Massimo, I think he's confusing locality. I mean, local conditions can be disrupted and the gravitational field of the Earth, but that doesn't change the fundamental structure of the universe, right?
No, that's right. That kind of event it would be certainly catastrophical, and this sort of stuff has happened in the history of the Earth. But we have no reason to think that sort of thing, which is really tiny at a cosmic level, would have any effect on sort of fundamental parameters in physics.
You're listening to Philosophy Talk. We're thinking about the laws of nature and whether they can change with Massimo Pigliucci from City University of New York.
In our final segment, we'll expand beyond the realm of fundamental physics to other scientific domains. If the laws of physics can change, what does that say about laws of biology, economics, or psychology?
Laws and the labyrinth of science, when Philosophy Talk continues. If all is erased and replaced, could that include the laws of physics and the basic laws of the cosmos? I'm Ken Taylor, and this is Philosophy Talk, the program that questions everything.
Except, of course, your intelligence. I'm Janan Ismail, sitting in for John Perry. Our guest is Massimo Pigliucci from the City University of New York, and we're asking, could the laws of physics ever change?
So, Massimo, we already talked a little bit about this vast labyrinth of the other sciences, but, I think I want to talk about this a bit. I think of science in its totality as this vast and layered labyrinth. You got physics at the bottom, and then chemistry, biology, neuroscience, psychology, economics, and to name just a few. I left out archaeology and anthropology. There's so many sciences. So how does the idea that the laws of physics might change? Let's grant that possibility. How would that reverberate up this vast layered labyrinth of total science?
Frankly, I would say not at all. And the reason for that is because, again, if we're talking, if the laws are, and this is very much a big if, but if the laws of physics are changing or are changeable, that certainly wouldn't happen at such a small scale, both temporally and spatially, as, let's say, the evolution of life on Earth. And even less so, of course, the evolution of our societies on Earth. So I don't think that would change anything in practice. Now, what that would change is the way we think about science, because all of a sudden, as we were saying earlier with Janin, all of a sudden we wouldn't have anything, fundamental physics wouldn't be fundamental in a, so to speak, fundamental way. It would just be a way to set boundary conditions on the other sciences. That's fine. But then we wouldn't know if those boundaries conditions are actually changeable for physics itself, and if we have ever actually reached the bottom of this thing, or even if there is a bottom of this thing.
One of the things that I've heard, an idea that I find really intriguing, is the idea that, well, what it means to say the laws of physics change is that in physics, as in biology, new things that were before kind of beyond the realm of possible suddenly come into possibility. And I'm wondering if that might change, precisely because of the role that you just pointed to of the laws of physics as setting conditions on what's possible.
No, that's right. Yeah. That is an intriguing idea. I mean, this is similar, at least, to the way in which Lee Smolin thinks about this thing. He thinks that causality is fundamental, and that, therefore, whatever happens in the universe, including the laws of physics themselves, are the result of causal interactions at a very basic ontological level. And what that means is that, as you just said, something new might happen as a result of previous causal interactions. Now, this is not at all controversial in biology. Biologists, for instance, talk these days of the evolution of evolvability, which is a fancy phrase to say that the mechanisms by which evolution itself takes place have evolved, they have changed over time. One very clear example is the invention of multicellularity. Once that life changed from only unicellular, one cell at a time, to multicellular organisms, that all of a sudden basically generated and made possible a whole new series of dynamics of causal interactions that made possible specialization of organs and made possible development, so on and so forth. So all sorts of new causal horizons opened up as a result of that invention, so to speak, that happened about 1.5 years ago, give or take. So that's an example. We certainly have examples within the other sciences of something like what you're talking about, of causality, previous causal interactions bringing about novel behaviors, novel possibilities, and then those possibilities change everything. They change the game.
It's a really interesting inversion that we used to think of, the physical laws as the paradigm, of what laws should look like. And now there's been this inversion where, in fact, physicists, or at least some physicists, are looking to biology. At least one physicist is looking to biology as, the model or the paradigm on which that we should conceive of the laws of nature.
Yeah, but I want to go ahead. I'm sorry, Massimo. Answer that.
No, I was going to say, this is interesting in a sense that actually kind of parallels the evolution of philosophy of science itself. Philosophy of science at the beginning of the 20th century was essentially philosophy of physics. That's it. The science was physics. And then, in the 1970s and 80s and then 90s, people started paying attention to, wait a minute, there is other sciences out there. And now, in fact, people see kind of things in reverse, that we're learning a lot more from the philosophy of biology now that we're learning from the philosophy of other sciences, including physics.
Well, because
there's a parallel.
Yeah, because biology deals with a different kind of system that arises in a different kind of way, and can't just be. You can't ask a biologist to just have physics envy because of the self-organizing. I mean, the universe is self-organizing, but in a different way than biological systems. I want to ask you about the scope of biology, because you said something that a little bit puzzled me, because you said the cosmic. If there were any change in the laws of physics, there was it would be on a cosmic scale and all that. But I think we think of biology in too limited a way because we're stuck on the Earth. And I actually think this is a general problem that kind of puzzles me. We're stuck on the Earth, but probably evolution has had 100 million chances to run throughout the universe. And I'm not quite sure that we know, how it would run everywhere under every condition. So that we just had a kind of local place where evolution has run once, but it could have 100 million run-throughs. And someday we'll discover that. Do you think there's a possibility that we might be surprised by, the 100 million run-throughs of evolution?
Oh, yeah, I think that's an excellent point. Yes, for sure. In fact, we don't really know. We don't have much of an idea of how evolution might have occurred on other worlds, under what conditions, when, and where. So, yes, we might very well be surprised. In fact, we may be surprised even if we find life on other planets or satellites of the own solar system, let alone the other side of the galaxy or the other side of the universe. The problem, of course, is that the chances that we are ever, or certainly anytime soon, going to discover life on the other side of the galaxy, those are pretty slim. So, we may learn a lot if we do, but I wouldn't bet my retirement pension
We've got
on
a
it.
caller, Pheneton in Palo Alto. Welcome to Philosophy Talk, Pheneton.
Hello.
What's your comment or question?
All right. First, I have a question, and then I'm going to give you an example of it. Now, this goes back to the more fundamental discussion. Now, how do you know that laws of physics are changing, or how do you know that the putative means by which you are observing or recording these phenomena are not changing? For example, my understanding of the Big Bang theory, and you're welcome to correct me if I got this wrong, is that at the initial moment of the Big Bang, that the laws of physics in terms of particles and how they held together was very different than it is, quote-unquote, today. So how do we know that, and how do we know that the laws by which we are observing those fundamental processes have not changed over whatever it is, 11 billion years?
Danan is dying to get in here.
No, I'm just thinking that's a great question. I mean, one of the things that happened with the development of relativity is we started to wonder how our clocks and our measuring rods and things like that, the things that we use to isolate the values of things like length and interval of time, how do we know that those are invariant, they work the same way at all speeds, and so on? Einstein denied that they did.
Backwards from that. You got to go backwards from that.
And where do you think that's going to lead?
I don't know.
Okay,
that's
so
why
Massimo,
I'm calling in.
Okay, thanks for the question, Fenton. Massimo, you want to weigh in on this one?
Well, so the problem with the laws of physics and sort of as they are now and then extrapolating them back in time all the way to the Big Bang, you have to assume that they are constant because otherwise you don't extrapolate anything. So the way we think we figure out, or we have a pretty decent idea of what happened immediately after the Big Bang and then up to now is precisely because we're making this assumption that the laws did not change. But that is precisely the assumption under question. Not only that, the other big question, which we haven't talked so much because we talked so far about parallel universes in the sense of the multiverse, but what about sequential universes? So one other idea is that every time that there is a Big Bang or and a new universe is created, then that's essentially an example of the either the lottery. Or new random combinations of laws come about, or there is what the Smalling calls this cosmic natural selection.
Right, that's what I was going to say. That plays a big role in Smollin's way of thinking about this, because to get evolution, you need replication and selection, and the replication is, as I understand it, the black holes giving rise to new. But I want to ask you a slightly different question. We're near the end, but I want to ask you a slightly different question because you alluded to it, and our caller Henry, our first caller, kind of alluded to it. Look, we get to dig around on the Earth and what we can observe from the Earth, and that seems like a pretty small slice of all the total evidence that there could be. How can we be so confident that we've got anything right? I mean, we seem very confident, and that's kind of amazing. How's that supposed to work? Briefly.
Well, that's supposed to work because what you can do is, you can do astronomical observations, cosmological observations, and you say, well, can I explain, if I simply extrapolate what I know about, locally on Earth, about the laws of nature, can I actually explain what I observe at a cosmic scale? And the answer, by and large, so far, has been yes. And so if you think about the laws of nature as physicists understand it, it's simply a model of the world. And I think actually that's probably, in my mind at least, that's the best way to think about any kind of scientific generalization or laws. It's a model of how the world works or how certain sections of the world work. And so you build this model based on your local data input, and then you expand and you apply it to a larger and larger sort of chunk of the world. And so long as the model holds, then you have no reason to believe that there is a problem. As soon as the model stops holding, that's why Smalling is talking about measurements of the gravitational constants, for instance, at very large cosmological scales. If it breaks down there, then there is something wrong with the model. Now, there may be the one thing that is wrong with the model. One of those things may be that some of the parameters that you thought were fixed were actually changing.
Yeah. So this is complicated stuff. I mean, and it's like a big change from the ancient world, because they thought, well, there's the stuff that holds up there and there's the stuff that holds down there. And we're like, no, the same laws hold everywhere. That's an amazing thing, don't you think?
It is. It really is an amazing thing. But now, ironically, perhaps we're beginning to really think that, yes, it's in a sense, it's true that what holds up there holds down here. But perhaps everything is changing, and maybe Heraclitus was right to begin with.
Yeah, maybe there's more places, more totalities than we imagine, in which, some of them don't hold. But you know what, Massimo, this has been a fascinating conversation. I'd love to have you back yet again and talk more about the epistemology of science. But at this point, I'm going to have to thank you for joining us.
Thanks very much for having me.
Thank you, Massimo.
Our guest has been Massimo Pigliucci. He's a professor of philosophy at the City University of New York. He's author of many things, including Nonsense on Stilts, How to Tell Science from Bunk. The conversation continues at Philosopher's Corner at our online community of thinkers, where our motto is Cogito Ergo Blogo. I think, therefore I blog. And you can become a partner in that community by visiting our website, philosophytalk.org.
Now, let's hear from someone who changes all the laws on the books. It's Ian Scholes, a 60-second philosopher.
Ian Scholes. Physics used to be apples falling and matter becoming energy, vice versa. Lasers and atom bombs and entropy. Quantum theory came along and threw physics into a cocked hat. Unless somebody was watching, then the hat became a wave. The concept of non-local entanglement has everybody excited. The idea being that a particle and a pair of particles cannot act independently of the other particle. Even light years apart, the effect of one affects the other instantaneously, if effect is even the word. Einstein thought this was a threat to the realist view of causality, calling it spooky action at a distance, and thought it proved that quantum theory was missing something. Quantum theory instead said to physics, no, you're missing something. And weird stuff has been happening ever since. Most recently, it has been surmised that the indeterminacy of basic stuff, as posited by Heisenberg, by Schrödinger and his cat, is not a bug of nature, but a feature. A particle state is not merely unknown, but undefined before it is measured. The act of measurement itself forces the particle to collapse to a definite state. It's not real until we look at it, or rather until it is looked at, or rather until something is done to it. One recent ramification of this is the possibility of time travel. I don't fully understand it, but because causality is pretty much out the window, there not only is no entropy in quantum physics, it can go forward and backward in time. This doesn't mean you will be able to be your own grandpa or kill Hitler in his kindergarten, but you can certainly make a quark spin counterclockwise, and that ain't nothing. I just read a book about how the emphasis in physics changed. It was called How the Hippies Saved Physics by David Kaiser, which they didn't really, but the book explores the strange interfaces between the counterculture movements of the 60s and physics. Very interesting book, not so much about hippies saving physics, but how quantum physics, or the stoned interpretation thereof, helped create hippies. What happened was, says the book, hard physics kind of hit a peak in the late 50s, and funding started to drop. The bloom had come off the rose for hydrogen bombs, space travel, missiles, etc. The more out there aspects of theoretical physics began to be explored by scientists banding together in coffee houses, bars, over drinks, coffee, marijuana, psychedelics. I'm surprised they didn't come up with one of those pig-monkey-human chimeras that Alex Jones is fixated on. But the ins and outs of quantum entanglement did lead them to wonder about faster-than-light communication, telekinesis, teleportation, and hence to an unhealthy interest in Uri Geller, remote viewing, sensing remote objects with the mind. It wasn't just hippies attracted to that stuff. The CIA was interested in remote viewing, allegedly, even sponsoring a study at Stanford University. Also, this new physics, so to speak, attracted Werner Erhard, founder of EST. He funded papers and symposia. There are strange best-selling books like The Tao of Physics, The Dancing Mouli Masters. Like Darwinism before it, being converted to social Darwinism, not quite the same thing, quantum physics was semi-subsumed by America with a trickle-down idea that reality is what you make it. What you make it. Hippies love that. It makes acid trips scientific. Motivational seminars love that. It gives you a self to help. Libertarians love it because selfishness is now scientific. And all this self-conscious solipsism is still with us today. Of course, it could be relatively new for all we know. Now that we know we can go back in time, who knows when we started thinking anything? We could just be going back and forth, making quarks run sideways, then forward again, then back, then getting stoned, forgetting all about it, doing it again. It's a vicious cycle. Or to look at it another way, it's the mystic cycle of gnosis, of which the ancient seekers dreamed. Selah, I gotta go.
Philosophy Talk is a presentation of KALW, local public radio San Francisco, and the trustees of Leland Stanford Junior University, copyright 2017.
Our executive producers are David Demarest and Matt Martin.
Our senior producer is Devin Strolovich. Laura McGuire is our director of research. Cindy Prince-Baum is our director of marketing.
Thanks also to Merle Kessler, Audrey Dilling, and Colin Peden.
Support for Philosophy Talk comes from various groups at Stanford University and from the partners at our online community of thinkers.
The views expressed or misexpressed in this program do not necessarily represent the opinions of Stanford University or of our other funders, not even when they're true and reasonable.
The conversation continues on our website, philosophytalk.org, where you too can become a partner in our community of thinkers. I'm John Perry.
And I'm Ken Taylor. Thank you for listening.
And thank you for thinking.
Do those look familiar?
How the hell did you get them up on that telephone wire?
When you understand the laws of physics, Penny, anything is possible.